So, this is lecture number 15 of our course on fundamentals of transport processes. In the last lecture, we had discussed the fundamental equations and the boundary conditions for the viscous flow. I am sorry, for the Navier-Stokes equations for a Newtonian fluid. Newtonian fluid, the stress is linear in the rate of deformation tensor, and the proportionality there is the coefficient of viscosity. Incompressible, the density is a constant, and therefore, there is no radial part of the rate of deformation tensor. The divergence of the velocity is equal to 0. In the previous lecture, we had discussed unidirectional flows. Many of the results that we had derived in the previous course on fundamentals of transport processes 1 using shell balances, where we explicitly selected a shell within the flow and wrote down the conservation condition for momentum, the rate of change of momentum and the sum of the applied forces. Those same results we had derived in the last lecture using the Navier-Stokes equations, which were derived using vector notations. In that particular case, for unidirectional flows, I showed you how these same equations, the Navier-Stokes equations, reduce to the far simpler equations that we have for the unidirectional flows in the previous lecture. Okay. So, in this lecture, we will start looking at special cases where we solve the Navier-Stokes equation in certain limiting situations. The diffusion dominated regime, that is when the Reynolds number is small. The convection or the inertia dominated regime when the Reynolds number is large. In those limiting situations, we try to solve the equations using some physical intuition. As I said, the Navier-Stokes equations, the mass and momentum conservation equations, they are partial differential equations in the velocity field, and they have two other important characteristics. First of all, they are explicitly time dependent. So, in general, at a particular instant in time depends upon the history, the previous velocity fields at earlier instants in time, and they are also nonlinear because of the inertial term in the conservation equation, which goes as u dot grad u. So, if you recall the Navier-Stokes equations as we had written in the last class, as we had written in the last lecture, we have two characteristics, two equations, one for the mass conservation, del dot u is equal to 0 or partial ui by partial xi is equal to 0. This is for an incompressible flow, and in addition you have the momentum conservation equation, rho times partial ui by partial t plus is equal to minus partial p by partial xi plus mu. Okay, the complete equations. They are time dependent and they are nonlinear because of this u dot grad u term. As of that, when you multiply the velocity by a factor of 2, not all terms multiply by that same factor, and therefore, they are nonlinear. Okay. We can consider this in different limits. As I showed you in the last lecture, if we scale this equation, we scale the velocity by a characteristic scale, the distance by a characteristic scale, okay, and due to this the time gets defined as t by L by u. If we scale it in this fashion, then we get the scaled equations as R e partial u I by partial t So, in this exercise I have scaled the pressure by the viscous terms in the conservation equation. That is, I define the scaled pressure as P by mu u by L. And if you scale it in this way, the Reynolds number is the ratio of inertia and viscosity. It can also be written as the ratio of convection and diffusion, where nu is the kinematic viscosity, the ratio of the viscosity and the density. It is also the momentum diffusion coefficient. So, if I scale it in this fashion, the Reynolds number multiplies the inertial terms of the conservation equation, and it gives me the ratio of inertia and viscosity. So, the first limiting case that we will consider is the case where the Reynolds number is small. Okay. So, small Reynolds number. Re is small compared to 1. Okay. So, in that case what you do is you neglect the entire inertial term in the mass conservation equation. Okay. And the reduced equations in the limit of small Reynolds number is called the Stokes equations. These reduced equations are del dot u is equal to 0 and minus grad p plus mu del square u is equal to 0, or in indicial notations partial ui by partial xi is equal to 0. Okay. So, those are the Stokes equations. So, first let us look at some idea of where one encounters this low Reynolds number regime. Okay. Re is less than 1, which implies that rho u L by mu is small compared to 1. Okay. For usual fluids, let us say take a typical fluid as water. Okay. For that, the density is of the order of 10 power 3 in SI units, kg per meter cube, whereas the viscosity is actually 1 centipoise, that is 10 power minus 2 poise, which is actually 10 power minus 3 in kg meter in the SI unit system. Okay, 10 power minus 3 kg per meter per second. Okay. So, in this case the Reynolds number is equal to 10 power 3 u L by 10 power minus 3 is equal to 10 power 6 times u times L, where u is in meters per second and L is in meters. So, you can clearly see that for common applications, okay, the length is of the order of a centimeter or so, the velocity is of the order of a centimeter per second to a meter per second. For those kinds of applications, the Reynolds number is clearly large, because I put a centimeter in length and a centimeter per second in u, I will end up with a Reynolds number that is 100. So, in common applications that we are used to, okay, our common everyday experience, the Reynolds number is actually large. Okay. The Reynolds number is going to be small only if the velocity is very small or the length is very small or both. Okay. So, for example, if you have a very slow flow, for example, in water treatment plants, in the flow through or in groundwater, the flow of fluid through the ground, for example, the velocity is very small, less than a millimeter a second, and the length scale in that case will be, for example, the pores between the solid particles there, the sand particles. That is a very small length, and therefore you will have a small Reynolds number. It is called the creeping flow regime. Okay. A very small length, okay, or a very small velocity. The motion of, for example, microorganisms in fluids. These microorganisms are very small length scale, typically about 100 microns or less. In that case, the velocity is also small, and therefore the Reynolds number is small. And because of that, many of the things that we that we are used to intuitively in our everyday experience do not work at those small length scales. The other system for which the Reynolds number can be small is for very viscous fluids. For example, glycerin, silicone oil, they have a viscosity that is about 1,000 times that of water or higher. In that case, though the density is still of the order of 10 power 3 kg per meter cubed, the viscosity is actually of the order of 1 kg per meter per second, and therefore, the Reynolds number becomes about 10 power 3 U L, where U and L are once again in meters and in meters per second. Okay. So, in that case as well, the Reynolds number can be small. So, there are very specific applications in which the Reynolds number is small and one can neglect the inertial terms in the conservation equation. And in those applications, our intuition that is built up looking at flows of macroscopic scale, for example, flows of water in streams and so on, that kind of intuition does not apply at these very small scales. Okay. And we will discuss the reasons why. These are the Stokes equations minus divergence of velocity is equal to 0 and minus grad p plus mu del square u is equal to 0, and these have to be augmented by the equation for the stress. Okay. So, the stress in this case tau I j is equal to minus p delta I j plus mu into this I should write as the total stress. It includes the pressure as well. Okay. This should be the total stress and includes the pressure as well. This is the stress, the force per unit area acting on the surface. Okay. So, these definitions of stress, pressure, the momentum equation and the mass equation completely specify the equations of motion for this system. The first thing you notice about this is that the equations now are linear. Okay. In the velocity and the pressure, the stress is linear in pressure and velocity, the momentum conservation equation is linear in pressure and velocity, and the mass conservation equation is linear in velocity, it contains no pressure. Okay. So, these now constitute a linear set of equations, and because of this one is guaranteed that there exists a solution and that solution is unique, okay, subject to well posed boundary conditions, of course. So, for these equations, if we have well posed boundary conditions, one is guaranteed that a solution exists for these equations and that solution is unique. Okay. The other property of this is what is called quasi steady. Recall, in the original momentum conservation equations, I had the partial derivative of velocity with respect to time. That was in the inertial term. We neglected the inertial term in the limit of low Reynolds number, and therefore, these equations do not contain an explicit time derivative. What that means is that the velocity at an instant of time can be determined purely on the basis of the velocity, that is the fluid velocity at an instant of time can be determined purely on the basis of the velocity boundary conditions and the stress boundary conditions at that same instant of time. So, if I have a particular configuration given to me at an instant in time with specified velocity or stress boundary conditions on the surface, the fluid velocity at that instant in time can be solved, can be obtained with that information alone. You do not need any information about the time history of the fluid flow, okay, what the fluid flow was at earlier instants in time. So, in that sense, for a given instant in time, if you are given well specified boundary conditions, you know what the velocity is everywhere within the fluid. So, that is the consequence of it being quasi steady. You are not solving a partial differential equation in time. You recall that when we looked at diffusion dominated transport in mass and heat transfer as well, the similar case was obtained. Okay. In that case, the equations were of the form d del square c is equal to 0, or alpha del square t is equal to 0. Okay. So, these once again do not contain any time derivatives, okay, and therefore, given a configuration and a set of boundary conditions at an instant in time, you can solve for that equation for the temperature or concentration fields at that instant in time without needing to know anything about the history of how the system got there. And physically, this is a consequence of the fact that when you assume that diffusion dominates, it implies that the diffusion takes place everywhere instantaneously. Okay. That is, you are assuming that whenever a temperature perturbation or a concentration perturbation is placed at some location in the fluid, the entire field responds instantaneously to that perturbation, because there is no time derivative. The assumption is that the response time of the entire field over the entire domain is fast enough that the information that there has been a perturbation at one particular location reaches everywhere instantaneously. Of course, that is not strictly true. It is true only up to a certain limit, and towards the end of the course we will try to analyze what will towards the end of this section we will try to analyze what that limit will be. Okay. But for the moment we will assume that the Reynolds number is low, and therefore, the equations are completely independent of time themselves. Boundary conditions could depend upon time. You could have a moving surface within the fluid, but the motion of that surface is instantaneously communicated everywhere within the fluid, because diffusion is a extremely fast process. Okay. So, that is the assumption here. So, that is the implication of a quasi steady set of equations. The other, the linearity, also has its own implications. Okay. One of the implications is that one can use linear superposition in order to find solutions to the equations. Okay. That is, when an equations are linear, let us say that I have a sphere that is falling in a fluid. I have a boundary condition on the surface of that sphere. The velocity of the fluid at the surface is equal to the velocity of the sphere itself, or any other object. It does not have to be spherical in general. Okay. Now, if I were to change the velocity of the sphere itself by a factor of 2, right, since the equations are linear, the velocity at each point in the fluid also has to change by that same factor. Okay. So, let us try to explain that in a little detail. Okay. Let us say I had some general object that was moving with some velocity u, okay, in some direction. It need not be spherical. What I solve is the equations del dot u is equal to 0 minus grad p plus mu del square u is equal to 0, with the boundary conditions u is equal to capital U on the surface. Okay, so, let us call this the surface S, that is the surface of the sphere S. Okay. Now, let us say that I changed the velocity of the sphere, the exact same object, it is not spherical in general, but the exact same object. If I changed its velocity to 2 times u on the same surface, S, I change the velocity to 2 times u. Okay. So, I have u is equal to 2 times u on the surface S. Okay. Since this is a problem in which the velocity has become 2 times, I will use the velocity u prime for this. Okay. U prime is the solution for the velocity field, with the velocity being 2 times u on the surface S. Okay. And I am solving the exact same equations. Del dot u prime is equal to 0 minus grad p prime plus mu del square u prime is equal to 0. Okay. One can easily verify that if I use the velocity field, u prime is equal to 2 times u. Okay. This exactly satisfies the equation. Okay. This exactly satisfies the equation. Okay. That is, I have to use a velocity field in which the velocity u prime for this new configuration, velocity is u prime here and velocity is u here, u prime is equal to 2 times u, and the pressure in this is equal to 2 times p. with this new velocity and pressure, the equations once again are identically satisfied. Okay. Because putting in u prime is equal to 2 times u in the mass and momentum conservation equation is equivalent to multiplying the original equations that I had here by a factor of 2, that is it. And since if something is equal to 0, you multiply it by 2, it is still equal to 0. So, therefore, you can get a solution for this by just multiplying the velocity at each point in the fluid by that exact same factor. Okay. You multiply the velocity at each point by that same factor, the pressure as well multiplied by that same factor, and what that means is that the stress is also multiplied by that same factor. The pressure is linear in the velocity, stress is linear in pressure and velocity. So, if I have a solution for this particular configuration for this particular velocity 2 times velocity u, I can get the solution for the velocity with boundary velocity 2 times u by just multiplying by that same factor by a factor of 2. So, if the velocity of the surface is doubled, the velocity of the fluid at each and every point within the fluid, the velocity and pressure are both increased by that exact same factor of 2. Okay. Does not have to be in the same direction. Okay. So, for example, if I take a configuration where instead of just taking the velocity and multiplying it by a factor of 2, I take that same object and multiply it by any factor. Okay. I can multiply it by any factor, multiply it by some factor alpha. Okay. So, that the velocity u is equal to alpha times u on the surface S. And the equations are once again the same, del dot u prime is equal to 0 minus grad p plus mu del square u prime is equal to 0 on the surface within the fluid. And you can easily see that the solution is one where the velocity and pressure are both multiplied by the same factor alpha at each point within the fluid. Okay. So, if the boundary velocities are multiplied by some factor, the velocity of the fluid everywhere is multiplied by that same factor. Okay. That factor could be positive, it could be negative as well. Okay. So, if I use alpha is equal to minus 1, that means that the velocity is reversed. Okay. That means that the velocity on the surface is exactly reversed. Okay. So, the velocity rather than being from left to right is actually from right to left. Okay, the velocity is minus u on the surface. Okay. So, therefore, I have u prime is equal to minus u, okay. And the solution, the equations are identically satisfied provided both the velocity and the pressure are exactly reversed at all locations. Okay. So, in this case both the velocity and pressure are both reversed at all locations. Okay. So, this is a valid solution of the equations. If I reverse the direction of the object of the velocity on the surface, the velocity at each point reverses. The same thing holds for stress boundary conditions, because stress is linear in both the pressure and the velocity. So, rather than imposing a velocity boundary condition on the surface, I could as well impose a stress boundary condition on the surface. So, if I have an object which is exerting a certain stress on the surface, okay, for example, if it is settling under gravity, that force per unit area is equal to the stress, the gravitational force per unit area exerted in the downward direction is equal to the stress. So, if the stress is doubled, that is, you increase the mass 2 times while keeping the shape of the object the same, then the velocity as well as the stress and the pressure at each point is doubled. If the direction of the stress is reversed on the object, then the velocity, the pressure and the stress at each point are exactly reversed. Okay. So, that is a consequence of linearity. And this leads to things that we would not intuitively expect when based upon our experience with macroscopic flows. Okay. For example, let us say we had the flow past some kind of a a rectangular object like this. Okay. Let us say we had the flow pass some kind of a rectangular object like this. Flow is coming in from the left, okay, with some constant velocity. Okay. And based upon our everyday experience, we would expect that the streamline coming in would go along the surface, and then it will come out like this, okay, because this is a bluff body. Okay. We would expect the velocity to go something like this with some circulation zone at the downstream edge. Okay. That is what we would normally expect based upon our everyday experience with macroscopic objects. This is not what happens at low Reynolds number when we neglect inertia. The reason is that this is inconsistent with the idea of reversibility and linearity. I told you that when the direction of the velocity is reversed, the direction of the velocity at the boundaries is reversed. The direction of the velocity at each point within the fluid is also reversed. And for this, this is not a reversible flow. How do I reverse the direction of the velocity on this at the boundaries? That means that rather than going from right to left, I would have the velocity at the boundaries going from right to left, okay, instead of going from left to right, and this is my object. The direction of velocity at boundaries is reversed, the direction of velocity at each point is reversed. Streamlines are the same, only the direction of arrows on those streamlines change. Okay. So, what linearity and reversibility were telling you is that if this is the solution, the streamlines that I would get for the fluid going from left to right, then for the fluid going from right to left, the streamline that I should get is as follows. Okay. The stream should remain exactly the same, only the direction of the arrows should change. Okay. That means that the streamlines remain exactly the same and only the direction of the arrows change. I should get a flow that goes like this, okay, with a circulation which is now going in the opposite direction. Okay, the direction of the circulation is opposite to what I have here. These two are clearly incompatible because this object has left-right symmetry. Okay. This object is clearly symmetric about this axis. Okay. Therefore, when I reverse the direction of the flow, the direction of the velocity at each point reverses. Okay. And if the object has to retain its left-right symmetry and the flow has to retain its left-right symmetry, you cannot have this kind of a velocity profile as a solution of your equations. Okay. Because when I reverse it, I do not get the same thing, which I would expect based upon symmetry. And we know very well that since the equations are linear, there exists only one solution. So, in the limit of very low Reynolds numbers, okay, the only kind of solution that one can have is actually one where either you have the flow going along the object and coming back down along the object on the other side. Okay. If this were the flow, then if I reverse the direction of the flow, I get back the same thing. So, this is consistent with the requirements of symmetry. Okay. So, in that sense, it is not what we expect at the macroscopic scale. Of course, you could also have a flow where you had circulation on both sides. Okay. You could, for example, have a flow that went something like this. Okay. You could, of course, have a flow which went something like this. This is also reversible. Okay. But however, in actual practice, you actually find that this second flow is not what you get. What you actually get is the first one. Okay. So, the requirement of linearity itself imposes some strict conditions on the kinds of flow that you can get. This is clearly not a flow that can happen at low Reynolds number, because it does not satisfy the condition of reversibility and linearity, whereas this is a possible flow profile at low Reynolds number. Okay. Similar things apply for other objects as well. Okay. If you have, for example, an object that looks like this, and when the flow is going from left to right, if you get, I am sorry, you should do it the other way. Okay. If the flow is going from right to left, you get streamlines that look something like this. Then for that same object, if the flow goes from left to right, for that same object, when the flow goes from left to right, you will actually get streamlines that go all the way back in down to the center of the object. Okay. You will get flow that looks something like this. You will not get separation from this object and a sort of circulation at the back in the limit of low Reynolds number. Okay. This is the only flow that satisfies the conditions of linearity as well as reversibility. Okay. You can also answer other simple questions for these kinds of flows. For example, let us say that I had two identical spherical objects. Two identical spherical objects settling under gravity. Okay. So, the gravitational acceleration was in this direction. If you had one object, it would of course settle at its terminal velocity. The question is, what happens when there are two? Let us assume that they are both aligned vertically with respect to each other in the same vertical line. Okay, we will assume that they are the same vertical line. They are aligned vertically with respect to each other. In that case, one can ask the question, to these two particles, does the one that is below settle faster? Does the one that is above settle faster? Or do both of these settle at equal speed? In other words, does the distance between the two objects reduce or increase as these are settling? Okay. Different people will give different answers for this question. Most people will say, based upon their experience, that the one that is above settles faster because it is following in the wake of the object that is below, and because it is in the wake, the resistance to flow is lower, and therefore, the one that is above will settle faster, and the distance between the two will decrease. So, this question can also be answered simply on the basis of linearity and reversibility. Both these objects are identical. Okay. So, let us for the moment assume that the one that is behind settles faster, while the one in front settles slower. Okay. What happens when you use reversibility? When you reverse the direction of the force, the direction of velocity at all points within the fluids is exactly reversed. Okay. So, let us reverse the direction of the force in this new configuration. I now have two objects, and I am reversing the direction of gravity. The direction of the velocity everywhere in the fluid is exactly reversed. That means the direction of the velocity is exactly reversed. Okay. This configuration, the one on the right, is exactly the same on the one as the one on the left, except that the direction of gravity has changed. Okay. So, in this case, what happens is this object, okay, this object in front, okay, this object in front is the one that is downstream, okay, that is further down along the direction of flow. Okay. Whereas, in the previous example, this object was the one that was downstream, further down along the direction of flow. Okay. So, on the left hand side, I am getting the solution as saying, okay, I had assumed, I had postulated for the configuration on the left hand side with gravity acting downwards, that the downstream object travels slower and the upstream object travels faster. So, that the distance between the two reduces. When I reverse the direction of gravity, okay, so that gravity is upwards, the direction of velocity at each point in the fluid reverses, and this tells me that the downstream object travels faster, the upstream object travels slower. Therefore, the distance between these two actually increases. These are clearly not compatible. Okay, these two results are clearly not compatible with each other. Okay. The only result that would be compatible when I reverse the direction of gravity was to say that both of these objects actually travel with the exact same velocity. Okay. If both of these travel with the exact same velocity, then whether I reverse the direction of the gravity or not, in this case the distance between the objects remains exactly the same as they are settling. Even when I reverse the direction of gravity, the distance between the same between the two remains exactly the same as they are traveling. So, the velocities have both got to be the same. So, the requirements of linearity and reversibility is telling you that when two identical objects are settling, they cannot travel at different speeds. They have to travel at the same speed. Okay. If you postulate that the downstream one travels slower, so that the distance decreases, when you reverse the direction you get the opposite result. They are not compatible. If you postulate that the downstream one travels faster, so that the distance increases, when you reverse the direction of force, you get the exact opposite. The only result that is compatible with the requirements of linearity and reversibility is that both of these identical objects have to travel at exactly the same speed in a viscous flow. Okay. So, those are kinds of simple results that you can immediately infer, okay, based upon the requirements of linearity and reversibility. Okay. Another interesting thing, swimming at the micro scale is actually very much different from swimming at the macroscopic scale. Okay. Small objects which swim have to use, they cannot use periodic motion to swim. Okay. For example, if I had a small microorganism, okay, which was using some flagella to swim. Okay. In macroscopic applications, we are used to just a periodic motion of these resulting in a thrust in one particular direction. Okay. In macroscopic applications, we are used to this situation where this periodic motion can lead to a net force. Okay. However, in the microscope for microscopic objects which typically swim at very low Reynolds numbers, this is not true, because let us say that you take a cyclical, okay, if this undergoes a cyclical motion, then if the object on the upstroke, if the object moves in one particular direction, okay, on the downstroke the velocity at each point is reversed to that in the upstroke. Okay. If it moves in a periodic manner, if this flagella moves in a periodic manner, so that along the upstroke it moves in one particular direction, along the downstroke the velocity at each point along that flagella is exactly reversed. So, that means that the velocity in the fluid at each point is reversed. Note that the velocity at an instant in time only depends upon the velocity on boundaries at that instant in time, in this particular case on this moving object at that particular time. So, the velocity at each point in the boundary is reversed between the upstroke and the downstroke. That means, the velocity within the fluid at each point is also reversed on the upstroke and the downstroke. Therefore, if this microorganism moves a certain distance along the upstroke, if the downstroke is exactly the reverse of the upstroke, it has to move an equal and opposite distance on the downstroke. Therefore, you cannot use periodic motion in order to for microorganisms to move in the limit of very low Reynolds numbers. They have to use something that is non-periodic, a cyclical motion for example, in order to move in one particular direction. This is very different from what you are used to at high Reynolds numbers. At high Reynolds numbers, because the nonlinear term, there is no reversibility, and because of that periodic motion there is no reversibility, and it is not quasi static either, and because of that a periodic motion could generate a thrust in one particular direction. Superposition can also be used to advantage in solving problems. Okay. For example, if I wanted to solve for the velocity field of a fluid which contains two objects which were moving in different directions. Okay. I could in general split this, the fluid velocity into two, I am sorry, the velocity of the object into two components. Okay. Okay. Okay, so I have two objects which are moving in different directions, which have a particular alignment with respect to each other. Okay, two objects which are moving in different directions with a particular alignment with respect to each other. Okay. The velocity of each object I can separate into two parts. Okay. One is the velocity along the line joining the centers of the two particles, and the other is the velocity perpendicular to the line joining the centers of the two particles. Okay. And I could use this to solve two separate problems. One is this one, where I include only the components of the velocity along the line joining centers, okay, plus a second problem where I include only the components of the velocity in the direction perpendicular to the line joining centers. Okay. So, first I solve this problem, find out the velocity field at each point in the fluid. Then I solve this problem, find out the velocity field at each point in the fluid, add up the velocities due to each of these problems, and I will get the solution for this problem, the velocity field for this one. That is, at each point in the fluid I can add up the velocity fields of these two problems. The result will be equal to the velocity field of the problem that I originally wanted to solve. That is because for these two, okay, the sub problems that I have, for these two, the velocity on the boundaries when I add these two up is exactly equal to the velocity for the first problem. And I know that if the velocity on the boundaries is added up, the equations are linear. So, if I add up the velocities for these two, the resulting velocity field also satisfies the equations of motion, that is the mass and momentum conservation equation. If they are satisfied individually by the velocity fields in these two cases, the sum of those two velocity fields also satisfies those equations. The sum of the velocity fields satisfies the equations, the sum of the velocity fields satisfies the boundary conditions. Therefore, the sum of the velocity fields is a solution of this original problem. Okay. So, that is the advantage, you can use linear superposition, okay, in order to solve the problem. An important point, when you use linear superposition, one has to be careful that the boundaries, okay, are all the same in all of those sub problems that you have divided the main problem into. Okay. Let me illustrate that. If I had a problem in which I had two objects, okay, I just showed you that you can divide into two sub problems where you separate out the velocities into two different components. So, what I cannot do is to separate out into two problems where I retain only one sphere in one case and I retain only the second sphere in the other case. This is clearly wrong. That is because the boundaries have not been kept a constant while I was dividing the problem into sub parts. Okay. I need to divide the problem into smaller bits in such a way that the boundaries, okay, all of the solid boundaries or the interfaces, okay, in each of the sub problems is identical to what was there in the original problem. You can separate out the velocity on boundaries into different parts. You can separate out the stress into different parts. For example, if you were prescribing a force on the boundaries, you could separate out that force into different parts. You could separate out the velocities into different parts, but you cannot just separate out the objects or the boundaries into separate parts. You have to make sure that in each of those sub problems, the boundaries that are chosen, okay, are exactly the same as those in the original problem, though the velocity conditions and the stress conditions can be separated out into sub problems. So, if you can do that, that gives you an important advantage. Okay. You can use this linearity and superposition in order to separate out a problem into multiple components and solve for each of those components separately. Okay. So, that is the advantage of having linearity of the equations gives rise to the possibility of superposition. Okay. Linearity of the equations means that you can use superposition to separate out a problem into smaller bits, then solve each of those separately. Okay. So, we have discussed some qualitative features, important features, quasi steady, linear, reversible, and use of the superposition principle to solve, okay, the equations, and you could get some simple results based upon just intuition. Okay. We did the particular case of two objects settling in gravity to show that the distance between the two has to remain exactly the same. So, let us proceed to try and solve these equations. Okay. The equations are of the form divergence of velocity is equal to 0 and minus grad p plus mu del square u is equal to 0. Okay. And just to recall, the equivalent of this in the case of mass and energy conservation were, for example, d del square c is equal to 0, or the equivalent one for the temperature conservation, for the energy conservation equation. In this case, of course, the diffusion coefficient does not matter. You are solving for the Laplacian of the concentration field is equal to 0. So, so in indicial notation, I would write these equations as minus partial p by partial xi. Okay. So, how do we solve these? As you would expect, we would try to reduce the equations to some kind of a Laplacian equation, and then we had discussed various methods in the fundamentals of transport equation 1 to solve this Laplacian of something is equal to 0 in order to find the concentration field or the temperature field. Okay. Turns out we can do a similar thing here, and that is by taking the divergence of this entire equation. You just take the divergence of this entire equation. Okay. If I just divergence of this entire equation, what I get is minus partial square p by partial xi square. Is equal to 0. Okay. In this second term here, I can interchange the order of differentiation because the x's are all independent variables. So, I can write this equivalently as is equal to 0. Then I have the first term here, which is the Laplacian of the pressure. Okay. Now, this term is clearly 0 from the mass conservation condition because it is the divergence of the velocity. So, it is equal to 0 because of the mass conservation condition. Therefore, if I take the divergence of the momentum conservation equation, I find that partial square p by partial xi square is equal to 0, which implies that del square p is equal to 0. So, basically you get that the Laplacian of the pressure is equal to 0 by just taking the divergence of the mass conservation of the momentum conservation equation. So, this del square p is equal to 0 can be used to solve the momentum conservation equation subject to appropriate boundary conditions. Then how do you solve for the velocity field? Okay. The way the velocity field is solved is to go back to the original equation. Okay. Yes, correct. Okay. So, this you can consider as an inhomogeneous equations for the velocity field u. Okay, you consider this as an inhomogeneous equation for the velocity field u, because I have already got the pressure from solving this equation, and I can put that into this equation in the gradient of the pressure here. Okay. So, I just use this solution to substitute for the pressure here. So, that gives me an inhomogeneous term in this equation. So, I have a linear inhomogeneous equation. Okay. And obviously, the solution can be separated out into two parts, the general solution as well as the particular integral. Okay. The general solution is the solution of the equation without the inhomogeneous part. The gradient of the pressure here is the inhomogeneous part. So, the general solution is the solution of del square u general is equal to 0. Note that the general solution is the one with which you enforce all the boundary conditions, and this is the one that contains the constants of integration. The second order equation, you would expect two boundary conditions at each surface, and this contains all the constants of integration. The particular solution is any one solution that satisfies the equation. Okay. It is any one solution. You can choose any solution. Okay. You do not have to have any, there are no integration constants in that. It is just any one solution that identically satisfies the complete equation. Okay. So, the particular solution is one that satisfies minus partial p by partial xi plus mu partial square ui particular by partial xj square is equal to 0. Any one solution that satisfies this equation. Okay. And it turns out that one can get a particular solution quite simply in this case. Okay. Since the gradient of the pressure balances the Laplacian of the velocity field, one would guess the particular solution to be of the form ui particular is equal to some constant p times distance. Okay. Because the gradient of the pressure is balancing the Laplacian. There are one derivative on the pressure, two on the velocity. So, you expect the particular solution to be of the form some constant times p times xi. Okay. Now, how do I determine the constant? I put this into the conservation equation. Okay. If I put this in, if I take one gradient of the velocity field partial ui particular by partial xj is equal to some constant into xi times partial p by partial xj plus p times delta ij. Okay. take another derivative, because I have the Laplacian of the velocity field here for the particular integral. So, I need to take another derivative, and I will find that partial u I is equal to c into, I will get x I partial square p by partial x j square plus 2 partial p by partial x j delta I j. Okay. First, I take the derivative of this term. Okay. First, I take the derivative of this term, okay, which gives me x I partial square p by partial x j square plus partial p by partial x j times delta I j, and second with this term, which gives me another partial p by partial x j delta I j. Okay. Therefore, and note that the pressure already satisfies the Laplace equation. Del square p is already equal to 0 over here. Okay. Therefore, this term, which is proportional to the Laplacian of the pressure, is identically equal to 0. Okay. Therefore, partial by partial x j of partial u I particular by partial x j is equal to 2 c partial p by partial x j times delta I j is just the gradient of the pressure, p by partial x I. Okay. Partial p by partial x I. Okay. And I know that partial minus partial p by partial x I plus mu times del square u has to be equal to 0. That means that this has to be equal to 1 by mu partial p by partial x I for the equation for the particular integral to be satisfied. Okay. Which means that the particular integral for the velocity is equal to 1 by 2 mu p times x I. So, the strategy is clear. Okay. I divide the velocity into two parts, a general solution and a particular integral. General solution satisfies the equation without the inhomogeneous term. Okay. So, that reduces to a Laplace equation. Particular integral is any one solution that satisfies the equation. In this particular case, I found one solution that satisfies the equation. Therefore, the total solution for the velocity is equal to the general solution plus 1 by 2 mu pressure times x I. So, I find the pressure by solving the Laplace equation, the general solution by solving the Laplace equation, then I put it together to get the final solution. So, this is the strategy we will use for solving the Stokes equations in the limit of low Reynolds number. As expected, we have managed to reduce it to two equations, each of which is a Laplace equation. There is a Laplace equation for the pressure, okay. There is a Laplace equation for the general part of the velocity, and the total velocity is the particular plus the general part. Kindly go through the solution procedures that we had done for the Laplace equation in the previous diffusion dominated transport lectures, and we will look at a different way of getting the same thing in this particular lecture. Okay. So, kindly revise that and come for the next lecture, and we will continue this in the next lecture. We will see you then.